Good morning. Today's lecture will be more classic image processing, and one of the topics that you probably start out doing your projects with when you get your data, and that's image enhancement. And I need to be on the right screen. Just a moment. That's it. So images are usually not perfect representations of what you observe. So there can be noise, there can be artifacts, and for that we can apply different filters in different domains, different ways. And if we do manipulations to images, we also have to verify that what we are doing actually makes sense. And for that we have also some literature to look at. And so typical books on that cover filters, Bernd Jene, Digital Image Processing, has a pretty good description on convolution filters. There is also John Ross, Image Processing Handbook, gives beautiful examples. And then we go into quantification, and that would be orientation quantification that you also can do with these filters. And the last part is about metrics, ways how we can quantify how good the modifications are on our images. Then there will also be some more publications throughout the lecture. And as usually, there is a bunch of modules that we need to load to run this notebook. And well, I'm not spending so much time on this, I think. Yeah, so the important thing are convolve 2D and Gaussian filter and midfield. Those are the main filters we are going to talk about. Yeah. Then there is this FLT, that's a whole package of different filters in scikit-image. For the full list, I recommend you take a look at the manual, which is online, and see what different filter types they are, and each is described with what properties you can expect from them. So, when you do a measurement, you have some impression or expectation of what it should look like. Let's say you did tomography of a rod and or ball, and then you would expect a homogeneous image like this. But thanks to the imaging system, you will have blurring is one thing, because you have an optical system that applies some blurring to the image. Then you have different noise types that can be added, and measurement artifacts that are also added. So what you actually measure is something like this, which is maybe not so nice, but that's the reality that you come across. And today's lecture is about how we can, from this one, at least can come closer to what we expect to see. So, yeah, I actually talked about that in the figure, but we have resolution, noise, contrast. That I didn't mention, that you can have more or less good contrast between different features in the image. And also that contrast in the image can be inhomogeneous thanks to fluctuations in the illumination. And then, of course, we have the artifacts. In tomography, the typical artifacts, the simple ones are rings and lines, but then you can have physical artifacts introduced as well, like beam hardening or scattering, which also add more complexity to the picture. These cannot be handled so easily with the filters I'm going to talk about today. The physical ones, I mean. So we have a typical image processing chain. We first acquire some images, then we do some enhancement, segmentation, post-processing, and finally we have the evaluation, And we are just focusing today on this one of these first steps to enhance the images. The rest will come throughout the other lectures, and yeah, we will see what we can do. So, for example, a little bit, this one will come to some part already next week, that one too. But so the next weeks will be a mix of segmentation and post-processing, and then comes the evaluation towards the end. So noise. What is noise to begin with? You could make a very abstract term that is that noise is all the information you don't want to have. But right now, in this lecture, we are more talking about random contributions to the image that disturb the features you want to detect. And that we, of course, want to get rid of. And there are different types of noise we can look at. We have, first of all, a very simple one. Every pixel has a statistical random distribution that is added to the information. So this is spatially uncorrelated. So there is no connection between this pixel and the next pixel. It's actually happening randomly from pixel to pixel. Then we have event noise. That can be small shots. That can be, for example, in neutron imaging, we get a lot of spots that are gamma photons hitting the detector. So we really have bright spots spread out. And that looks more like this salt and pepper style. And that is, you have the main background, the main image, and then all these outliers pop out like salt grains or snowflakes or something like that. And the last one is structured noise. That is when the noise is driven through some optical system. Like this one, you can see that this noise is really from pixel to pixel, and this is more blurred, blobby noise type. And that you can get, for example, if you have radiation detectors, the scintillator doesn't convert the photon exactly on a point, on a pixel, but there is some kind of flare or blow up that produces an unsharp hit. And then, of course, you have, on top of that, you have the optical system, which may not be so sharp as you would like it to be. And with that, you can get this structured noise effect. The noise models we are usually talking about, the first one, which is mostly coming up, is the Gaussian noise. It's a very easy model, and you see it a lot. Everybody tries to go to the Gaussian model because it's the easiest one to work with. All the math comes out very nicely when you work with it. And it's, in principle, you have a symmetric bell-shaped distribution. You probably already know it from your math classes. And then there is an average value and a standard deviation. Average value determines the intensity value, so gray level intensity value, and the variance, how much it fluctuates around this value. And the good thing is also, thanks to the law of large numbers, most distributions can actually also be pushed into this one if you have sufficiently many observations. So, and the next one, which this doesn't fit. Let's see if I can. So, there it is. The next one is the Poisson noise. And that's actually a more realistic noise model for imaging systems because it's a counting process that it reflects. And when we are looking at photons of different kinds or other particles, they are usually arriving in the pixel in a certain amount, and that's this counting process that you have to do. And Poisson noise is a bit uglier to work with, actually. And the thing is, if you have very few counts, it's a very skewed distribution. And the more counts you get, the more symmetric it becomes. Another feature of this distribution is that the noise variance is the same as the average. So when you have many counts, that means you will have a great value for the average. Then you also at the same time have a great value for the variance. So it changes with the intensity like that. And here is an example where you have the Gaussian noise. It's uniform. If you go along this sine curve here, you can see that the variance is constant no matter where you are in the intensity. But if you look at the Poisson noise, I hope you can see that this distribution here is a bit wider than that one. At least the bar for the standard deviation is here longer than this one. And if you just extract the noise term, you can see here that it is more or less a constant deviation level, and here it has a little waist around here and blows up around here. So this is what you actually have within the image, that you can have regions. If you have Poisson noise, you can have regions which are kind of lower noise amplitude and regions where you have greater noise amplitude. And next model I mentioned was salt and pepper noise. That's more probability distribution. So you have outliers. Of course, you can have different amplitudes on these outliers, but it's more about the frequency of these outliers. So let's say you have a black and white spot. So you have negative spots and positive spots is what this model is showing. So if you are below some threshold lambda 1, it will be a -1. If it's in this interval, you have a 0, so no outlier. And then you will have the last threshold is when it's above the threshold. It can be driven by any noise distribution, but in this case, I just take a uniform distribution. So all observations are equally probable. And the noise fraction is lambda 1 plus lambda 2. And some examples of that you can see here. So here I set lambda 1 1% at 1% and lambda 2 at 99%. So that means our noise fraction is 2% here. Then you can see that you have some blacks and whites in the image. And then when you go up to the noise fraction of 10%, yeah, then it starts getting a bit harder to see things. And even going up to 20%, then it starts getting obscuring the true information a lot. Now in this case, the true information is just a 0, so it's nothing exciting. But you can imagine if you have some measurements and a lot of these outliers, it can be quite disturbing. Measuring the noise, how strong the noise is, needs some kind of metric, and the most used metric is the signal-to-noise ratio. There are very many different definitions of it, but in signal processing, we usually talk about the average value, so that is the average intensity divided by the standard deviation. So you divide the intensity by how much it fluctuates. And a way to see it is here. You have, for example, for the Poisson distribution, it nicely comes out that the signal-to-noise ratio is proportional to the number, square root of number of counted events. And in an imaging system, you have different ways of modifying how many events you get. So one way is you have some flux, so you can modify the flux of the source, having a stronger or weaker source. That will have an effect. And then you also have the exposure time. And you can see here in this example, I tried different exposure times. I think it was a tenth of a second up to 10 seconds. So it's a quite big span between these. And you can see here in the beginning, you have quite a noisy image. And if you expose 100 times longer, you end up with a much better signal to noise ratio in the image. So, and the important thing is you can also here see how it's proportional. Exposure time is proportional to the square root of n, so the number of events that were captured. A different way to also increase the number of events is to change the pixel size. The larger pixel you have, the larger bucket you can collect pixels in or events in, and with that you can also improve the signal to noise ratio. So those are the three main ways: changing the flux, changing the time, and changing the pixel size. And that, for an imaging system, are the ways you can improve the signal to noise ratio. And when you are playing with these in your, yes?
Just to clarify, Gaussian and Poisson noise will not depend on the values of the surrounding pixels, right?
No, they don't. In a real system, you will see a spatial dependence because you have all the blurring. But in an ideal system that each pixel is an observation without, it should be without dependence on the neighbor, then it's shouldn't be, yeah. But yeah, in the reality, you will have some blurry effect with a Poisson-related distribution. Yeah, here are some tools that you can use if you want to play with it in Python. Everything comes from NumPy, so there is a package in NumPy called random, and there you can get the Gaussian distribution, uniform, Poisson, and I think a handful of other distributions if you would like to do that. For doing the statistics, you can also use these functions. And so you have mean, variance, standard deviation, min, max, median, and rank. Some of these you can actually apply directly to the NumPy arrays. So you can just have your array variable dot mean, for example, and then you get the average value. So there are two ways of accessing that. So you could either do np mean x or x dot mean. So you can use both of those. So now we know that our images are not so nice as we would like them to. So let's go into filtering and how to improve that. And first of all, what is a filter? So it's kind of a machine that enhances the information you want to have and try to suppress the information you don't want to have. Sometimes it does. Usually you can do one of them, and that gives a side effect that the other one appears to be enhanced or suppressed. But the ideal filter should actually do this enhancement without altering relevant features in the image. And that is the problem that we often fight with when we do filtering, in particular to do denoising. And filters have different kinds of characteristics depending on which information you want to amplify or suppress. And the typical filters are two types. One is the low-pass filter, which enhances slow variations in the image, while rapid variations are suppressed. So in this toy example, you can see that there is a slow variation, and there is something that rapidly changes. And with a low-pass filter, you should ideally get this slow variation field without any disturbance from the rapid part. The opposite is then, of course, the high-pass filter, and that one enhances the rapid changes in the image, and the slow changes are suppressed. What I mean, the word low and high pass actually relates to the frequency domain, because these are spatial frequencies, and I will talk more about frequencies later. But in principle, the slow fluctuations are low frequencies in the image, and the rapid fluctuations are the high frequencies. So that's why we say high pass means that we have all the high frequencies, and low pass is that we have all the low frequencies in the image. The basic filter models are usually based on convolution, so it's a linear filter, which essentially follows the convolution operation. And if you would like to draw it in a box flowchart, then you would probably do something like the image F comes through some filter kernel, and the result is the kernel convolved with the signal. And in reality, we have discrete images, so this integral turns into a sum. And before I come to that, I'll show you some typical kernels. This filter system functions are called kernels, and the typical ones that you start using are the box filter or mean filter, also called uniform filter, depending on which literature you use. And then you have the Gauss filter. And this Gauss filter should not be confused with the Gaussian noise. It's just that we use the shape of the Gaussian distribution, and not that it's particularly a good one for Gaussian noise. So they are only related because of the shape of the function. So anyway, as you can see, the uniform filter has the same weight for all positions, and the Gaussian filter has more focus towards the middle of the kernel, and then it tapers off the further away you get from the center. And how it's working if you apply it, here I show some examples with different signal to noise ratio, and I'm applying a Gauss filter to that. The noise, by the way, is actually Gaussian, but so here you can see we have signal to noise ratio 100, so essentially no noise at all. Then we add noise to a signal to noise ratio 10, 5, and 2. And you can see what signal to noise ratio 2 does. It almost completely obscures all relevant information in the image. And then so this is essentially also just directly the image. Next step, we have the width of the Gaussian kernel is 1. And then you can see that the first one gets a little bit blurred. The next one, you can see the effect that the noise is actually suppressed to some degree, and also, again, a bit blurred. At signal to noise ratio 5, it's getting better, but still you miss a lot of features because the noise is actually obscuring it. And for the lowest signal to noise ratio, the only thing you can see that there is something, but you can't say what it is, so you can more or less just use it to detect the main body of this feature. Going on, using a really wide kernel, sigma 3, then you can see that it blurs the image so much that you can't even distinguish these ripples in the arm. That is gone. And also the ribs, they are getting more and more blurred out. You can see that there is an eye, but that's it. It's very good against the noise, as you can see. Even going to signal to noise ratio 5, you don't see any noise at all. At signal to noise ratio 2, you can actually see that there is some inhomogeneities in the noise. But here, you can actually still see that the eye could be here, that there is an arm here, but the rest of the structures, they are gone. But you can, with the help of such a large filter, you can actually suppress very strong noise as well. So, how it's done. A convolution, as I said in the beginning, is from this convolution integral, but as we have discrete images, we are more talking about sums, or weighted sums actually. And in this case, we have just a box filter. So we take all pixels, so in this case, I had a 3x3 filter kernel, all once. So I take all these pixels, sum them up, compute the divide by the number of items, and then I get a number 3.7, which is the average value of this neighborhood. And that is then placed on the new pixel in the filtered image. And that is repeated for every pixel. And you never have to write this yourself, unless you enjoy writing the code. But otherwise, there are functions for doing this kind of calculations, and you should probably use them because they are most likely more efficient than what you can write yourself in short time. And if it would be, for example, a Gauss filter, then you would have actually multiply weights here for each pixel value, and then do the summing, which would be the sum of the weights instead. And yeah, one more thing. Mostly, I recommend to use kernels with an odd number of elements, because that means that you have the central pixel is unique, and it's placed here in the middle, unless you tell it to do something else. If you have an even number, then you don't know where the middle is. So the effect is that your your image will be shifted by 1 pixel somehow in one direction. So when you do convolution, I think it's best that you use the odd number of elements in the kernel. An interesting mathematical feature is the so-called Euclidean separability, and we can use the associative and commutative laws to achieve this. So convolution, if you have convolution of 3 different parts, you have A convolve B convolve C, that is the same, so you would convolve this block first, and then with this, would be the same as convolving that one with that block instead. And you can always flip the order of the operators. So this is something you can use if the kernel can be split into several parts. And the splitting is shown here. So for example, the box filter, which is 3x3, can be split into 1 vertical part and 1 horizontal part. And even the Gauss filter can be split in this way. So you can have a convolution of first a Gaussian in the x direction and then a Gaussian in the y direction. So why do this? It's just some mathematical trick, or what is it? Now, actually you can gain a lot of speed with doing this, because, let's see, if you do the 3x3, typically, you would have 9 multiplications and 2 additions. But if you do the splitting in this way, you can instead do 6 multiplications and 4 additions, and that will save you a lot of time in your processing. It becomes more interesting if you do it in 3 dimensions. So instead of doing 3x3x3, which would give you 27 multiplications and 26 additions, then instead you can do it in 9 multiplications and 6 additions. And in particular now, going to the 3-dimensional analysis, if you would have, say, a filter kernel which is 5 cubed, then you start seeing a real remarkable change. I did some tests with these small kernels using Python, and I was a bit disappointed actually, because with the small kernels, it was slower to do the separable thing than doing it directly as one kernel. The reason is the overhead in the function calls that made it more expensive to do 2 calls to the filter function than to just do a single one. So that is something you have to explore. Where are the limits? How large kernels do you have to have before you switch to the separate kernel approach? Another filter which is also of low pass type but is not a linear filter is the median filter. And again, you define some neighborhood region. And in this case, what you do is you take all the numbers from that region that you have defined. Then you sort them and take the middle one. So that's actually that you take out the median for every pixel neighborhood and place that instead in the place of the new pixel. And that gives you, again, a low-pass effect. And I will show you some examples where you can gain using the median filter over a convolution filter. And if you have an image with a lot of spots, so salt and pepper noise, and try to apply a Gauss filter on that, the only thing you will do is that you will get a spatially correlated, a little bit better, but mainly a spatially correlated noise instead. But if you would apply a median filter to this salt and pepper noise, then you would get a clean image. So if you have outlier noise, this median filter is the better choice. And on the other hand, if you have Gaussian noise, the improvement is not that much better, actually. So for that kind of noise, you have to, it's not so certain which kind of filter you should use. And an example how we can use the median filter is when you want to remove spots from images. And this is something that is very common in my typical images, but also in other techniques. We have these spots. It can be really spots, as I can show here, but it can also be small streaks like this one. And they vary a lot in size, intensity, and frequency. So it's not sure exactly what we are looking for. And the different ways we can work with is to use a low-pass filter, a median filter, oops. And let's see if I can get rid of that one. I couldn't. Let's just take the first alternatives and see what happens. First, low-pass filter. You will reduce the amplitude, but you will smear out the spots. So low-pass filter is not really a good choice. The median filter would take out the spots, but it will also introduce some blurring to the image. And that means we would lose image sharpness for later processing, and we don't want that. So instead, what I'm proposing here to do is to have a little algorithm that first detects the spots and then replaces them. And with that, we can get much better results. So the spot cleaning algorithm is outlined like this, where we have the original image going in. We do some median filter, and you can see here that the spots are gone, but maybe also that it's a bit blurred. Then by subtracting the median filtered from the original and also doing the absolute, we can extract where the spots are. And then by thresholding in this image, we can determine is this an outlier or is it not? If it's an outlier, we replace that little region with the median value. And if it's not determined as an outlier, then we just leave it as it was. And finally, we get a cleaned image, which has preserved edge sharpness and the spots are gone. The parameters we have here are two. One is the width of the filter kernel. That decides how large spots we can cover. And the other one is a threshold level. What is the level of these? Yes?
How would you determine these parameters, like especially K? Is this trial and error or is there mathematical based formulas?
Mostly it is, I would say, trial and error. You can do it based on the histogram, because if you look at the histogram of, that's actually next week's lecture, but anyway, if you look at the histogram of this detection image, so that's the, whoops, the, let's see if I can get there. Yeah, so this would be the detection image, and if you look at that one, it looks very much like, so you have a very high peak here, and then it goes slowly out in almost nothing like this. And then it's about finding a spot around here where you'd say, this is the level that I have as my threshold for saying this is an outlier. There are different algorithms to do this, but let's keep that to a next lecture. Now, one way you can also do is you can, so there are algorithms to search for this, and the other way is look at a cumulative histogram. So then you take the cumulative result, and then it looks like this. And then you can say that if you reach, say, 95% is a reasonable value, then you can say that everything beyond 95% is an outlier. That's another way of doing it. So, looking at the output, and now actually you can also see what is the effect of doing this. When I introduced the different filters, you can see that you have the original, where we have some spots. If you apply the box 5 by 5, which is needed to get all these, you can see that there are clear blobs, square blobs even, around where the spots were. So that is clearly not a good idea. And you also get quite a lot of blurring, because it's a large filter kernel. Then you can do a median filtering, and it does remove all the spots, but you can also see that all the structures that were in here, they are reduced a bit in sharpness. And by applying this cleaning algorithm, you have essentially the original image, but without these spots included. And if you look at the difference between original and filtered, it looks like this. We also can see that there is a lot of noise reduction or structure reduction. You can see there is a little bit of stripes and lines in here that vanish. That effect is less when you do the median, because median is a bit more edge preserving than the Gaussian filter or the box filter. And if you do this cleaning algorithm, you can see that it's only the spots themselves that are removed. So this is the way that it's also done in, for example, ImageJ. If you do remove outliers in ImageJ, this is in principle the algorithm that you're using. They are, I think, using a round footprint of the median filter, because they're talking about the radius. But otherwise, it is the same, but there it's a trial and error approach, so they don't have an automatism to find where the threshold should be. Then in ImageJ, just as a little warning, there are two ways of removing the outliers, and the way called despeckle, that is just a plain median. So it's not really very useful. So avoid that one if you want to remove outliers. And yeah, let's start a bit about the high-pass filters. So until now I have talked about low-pass filters, and we could see that they smooth the image, but the opposite would be the high-pass filter. And the typical high-pass filter you have, they are can be related to the gradients and even the Laplacian. And there are different ways of computing the gradients. The very simple one is just subtracting the neighbor with the following one and divide by 2. So that's a very simple definition of the first derivative. But it's from the signal point of view, and in a discrete world, it's not so good. So there have been some efforts in producing some optimal kernels, and this is more the recommended kernel to compute the gradient of an image. Then you can also use the compute the Laplacian, and it has been quantified to this, and you can see that there are positive values surrounding the central pixel, which has a great negative value. And this value is actually the sum of all the others. And I will show you later how we can use them. So of course you can use them in physical modeling, but there are other uses for them as well. Then there is also one called Sobel, which is the magnitude of the gradient. So then you have to do 2 filterings, one direction X and one direction Y, or possibly also in Z, and then sum them up together. And looking at a gradient example, what we can see when you apply a high-pass filter are mainly edges, because edges is the region where you have the most bundled energy in the high frequency range, because you need very many frequencies, high frequencies, to describe a quick rise in the data. And looking at this structure, which by the way is a soot particulate filter, or a little cut of it, and here you can see the soot and the ash in the images. But right now we are more interested in this nice grid-shaped structure, and you can see that if you compute the gradient here, you have always on rising side and falling side, you have a dark track and you have a bright track, and that is because the derivative changes sign depending on if it's rising or is falling. And if you do dx, you see all the vertical structures. If you do dy, you see all the horizontal structures. And in this case, I use this filter, and it's actually described in the book by Bernd Jene that I mentioned before. Then we can use these gradients to detect edges. And now I actually took it one step further. So previously we just looked in separate directions, but the Laplacian and the Sobel, they actually bundle up both directions in a single equation, or yeah. And when you apply the Laplacian, you can see here that you have a little change here at the edge, transition from dark to bright, and no matter in which direction we go, but it's always from low intensity you have first a dark part and then it goes up in the bright part. In the Sobel filter, which is the absolute, then you always, the edges are always represented by bright values. But depending on your edge detection algorithm, you can select which one is the most suited for you. And yeah, filters can also be used in machine learning. So you probably have heard about the convolutional neural networks, and here comes our filters also again into play, because each of these nodes in the network is a different kind of filter kernel that is applied and then weighted together into the final answer. So in the beginning, you can see maybe there are some different changes, and after a while, you can see that the kernels get more and more focused towards some specific structures, and then in the end, in this case, it was meant about finding traffic signs, and the output are first saying it is a traffic sign, and afterwards which speed it tells to be. Yeah, and with that, I think it's time for break, and then we go on to frequency space and talk more about what I meant before by quick and slow changes in the images.